Hello, today we're going to discuss 6.3 area and the definite integral. We discussed indefinite integral in 6.1 and 6.2. We know the indefinite integral of a function is just the family of antiderivatives of the function. In this section, we're going to introduce a new type of interval, the definite integral, and we start from the area problem. Let's find the area of the region on the graph of f equal to x squared on the interval from 0 to 1. So this is the parabola, and we need to find the area on the parabola from 0 to 1 on the x-axis. And we don't have any formula to compute it. So let's try to find the approximation of this area by drawing rectangles in the following way. We start from partitioning the interval from 0 to 1 on the x-axis into 4 subintervals. There are the interval from 0 to 1/4, the interval from 1/4 to 1/2, the interval from 1/2 to 3/4, and the interval from 3/4 to 1. And then we approximate the area on the curve by sum of rectangles using each subinterval as the base of the rectangles. So we just draw rectangles from the subintervals. And the value of the function at the midpoint of each subinterval as the height of the corresponding rectangle. So let's look at the graph. So in this graph, the curve of y equal to x squared is drawn. And we want to find the area under the curve from 0 to 1 on the x-axis. So what we do, we divide the interval from 0 to 1 on the x-axis into 4 subintervals, as shown in the graph. Then we pick up the midpoint of each subinterval and then evaluate the function at those x values, and we got the 4 red points on the curve. And then we use the y coordinates of those points as the heights of the rectangles. So we got 4 yellow rectangles as shown in the graph. The midpoint of the interval from 0 to 1/4 is 1/8, and the height of the first rectangle is f of 1/8, which is 1/8 squared. I mean, we got 1 over 64. We know the function is y equal to x squared. The midpoint of the interval from 1/4 to 1/2 is 3/8, and the height of the second rectangle is f of 3/8, which is 3/8 squared. We got 9 over 64. The midpoint of 1/2 to 3/4 is 5/8, and the height of the third rectangle is f of 5/8, which is 5/8 squared. We got 25 over 64. And the midpoint of 3/4 to 1 is 7/8, and the height of the fourth rectangle is f of 7/8, which is 7/8 squared. We got 49 over 64. So we got the height of each rectangle, and then we can compute the area for the rectangles and get the approximation of the area on the curve. So the area of the first rectangle is 1/4 times f of 1/8, so that's base times height. We got 1/4 times 1 over 64. The area of the second rectangle is 1/4 times f of 3/8. We got 1/4 times 9 over 64. The area of the third rectangle is 1/4 times f of 5/8, which is 1/4 times 25 over 64. The area of the fourth rectangle is 1/4 times f of 7/8, which is 1/4 times 49 over 64. So add those areas up, we got the total area of the 4 rectangle, and then we can factor out 1/4 from all the terms. And then sum up the heights. We got the 1/4 times 84 over 64, and we can convert this number into decimal to get 0.328125. So this is the area of the rectangles. Now we can cut the interval from 0 to 1 on the x-axis into more subintervals as we just did, and hence form more rectangles in the same way we did for n equal to 4. And obtain better approximations for the area. So in the table, you can see the area we obtained by cutting the interval in different numbers, n. So n equal to 4, 8, 16, 32, 64, 100, 200. As you can see from the table, the area of the rectangles will approach 1/3 as we increase the cutting n. So the limit of the area seems to approach 1/3, and we speculate the area of the region on the graph of f equal to x squared on the interval from 0 to 1 to be 1/3. All right, so we can generalize this idea into more general functions. So in general, to find the area of the region on the graph of f on the interval from A to B, we divide the interval from A to B into n subintervals of the equal length delta x equal to b minus L over n. And then we pick an arbitrary points x1, x2, x3 to xn from the first, second, third, and the nth subintervals, respectively. So you just pick up any point in each subinterval, and then evaluate the function at those points and use the y coordinates of those points as the heights of the rectangles. The area on the graph of f on the interval from A to B can be approximated by the summation of the areas of the rectangles as we just did. So that will be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x2 f of x and delta x. All right, the height times the width. So we can factor out delta x. The above summation is called the Riemann sum, and the limit of the Riemann sum gives the exact value of the area of the region on the graph of f on the interval from A to B, just as we did for the example. And this limit is called the definite integral of f from A to B, and is denoted by this symbol. So the definite integral is the area under the curve. Furthermore, A is called the lower limit of integration, and B is called the upper limit of integration. So this is for today.